lecture, we're going to look at nonlinear systems and their phase plots. So let me create a new file and let us see what the even natural evolution. So in the previous few lectures, we have looked at the behavior of linear systems, and the behavior of linear systems near a fixed point was decided by the nature of the eigenvalues and eigenvectors. So if we have real eigenvalues, then well, if the eigenvalues are real, so we can either have a stable node, an unstable node, or a saddle node, and this depends whether both of the eigenvalues are negative, both of them are positive, or either of them is positive and negative. Then we have seen that the behavior for the case of imaginary eigenvalues either has a spiral inwards depending on the real part, or a spiral outwards depending on whether the real part is positive, or a closed orbit. This is the case where the real part is equal to 0. It is purely imaginary. So now these ideas can be used to analyze nonlinear systems as well. In particular, if we have fixed points, then we can perform linearization near the fixed points and see the behavior. So let us start with an example. So x dot is x plus e to the power minus y, and y dot is equal to minus y. So this particular differential equation, it's an example from Strogatz, and let us see how the phase plot for this equation looks like. And the thing about the phase plots is we can reuse much of the code that we have made for the linear part. We just have to change these particular so-called velocities. So this specifies the vector flow, and our task is to specify this as the new set of velocities. And finding out the trajectories is no different. We can have in the phase portrait, if this is x and this is y, we can have different initial conditions, and we can have the evolution of trajectories, which are in this case governed by this nonlinear set of equations. There is no analytical solution available. Even if there is some analytical solution available, it is often quite difficult to make sense, or rather to interpret that equation, because it is not clear as to how the variation will occur explicitly. Okay, so let us go to the lecture and let us copy this, because we'll need this. In fact, for the 3D plots, we'll require Maya as well, Maya V as well. Alright, we need to import this, and let us import this particular plot, with this particular cell. In fact, let me run this to see everything's fine. Okay, everything is fine. So let me now change the flows. So this is x plus e to the power minus y, and this is simply going to be minus y. Alright, let me change this as well. Let us first see how the flow looks like. Okay, so let me get rid of these eigen vectors that we had plotted. Alright, so this is how the flow looks like. Okay, so let me increase the density to 1.5. Okay, so right over here, let me take this plot to our notebook over here. Okay, so let us try to make sense of this. So if you have a close look, there appears to be a stagnation point over here, meaning streamlines go like this and like this and like this and like this. So things appear to be converging from in this particular line, and it appears to be diverging along this particular line. Alright, and these two sets of curves appear to demarcate the entire phase plane into this kind of behavior. So as time goes to infinity, as t goes to infinity, the trajectories are attracted towards the unstable manifold. So this appears to be the unstable manifold. While this is the stable manifold. Okay, so as time goes to infinity, we see that they are indeed going towards the unstable manifold. So this point appears to be a non-linear version of the saddle point. Okay, it appears to be the non-linear version of a saddle point. So now let us try to make sense of this particular equation. Why does it look like this? Obviously, what are the fixed points of this system? So the fixed points correspond to x dot equal to 0 and y dot equal to 0. That means y equal to 0. Okay, and when y equal to 0, is equal to minus 1. So at x minus 1 and y 0, we do see that uh, there is a saddle point. Okay, this corresponds to minus 1 comma 0. Alright, so that explains the. So what about the behavior? What about the behavior of that point? Okay, so why does it appear that this particular point behaves like a saddle node? So saddle node, it implies that one eigen direction towards it is stable and the other is unstable. So let us look deeply into the structure of the vector field in the vicinity of the fixed point. Actually it is minus 1 comma 0. Okay, so let u be minus 1 plus or rather x plus 1 and v be equal to y. So in fact, let us look at the, let us demarcate it, denote it by x star y star, so that we can keep things symbolic until we make the final substitutions. So let us choose a variable x as x minus x star and v as y minus y star. In that case, u dot will be x dot minus 0 and v dot will be y dot minus 0. So u dot is equal to x dot and v dot is equal to y dot. So u and v are uh, sort of the behavior. So if this is the fixed point, it's the behavior in the vicinity of the fixed point. Okay, near x star y star. So then this is equal to, so if I write down x dot equal to f of xy and y dot is equal to g of xy, then I can write this down as f of xy and I can write this down as g of xy. Now f of xy, I can write it in terms of this as f of x star plus u and v y star plus v. Okay, similarly I can write down v dot is equal to g of x star plus u and y star plus v. Alright, so now we can use Taylor series expansion to write this as f of x star y star plus del f del x at x star y star times u plus del f del y at x star y star times v. So this is going to be u dot plus order u square, v square and uv terms. So basically quadratic terms. Similarly, we can write down v dot is equal to g of x star y star plus del g del x times u plus del g del y times v plus order of u square, v square, uv. So essentially, we can remove this term and this term because x star and y star are fixed points. It naturally means f of x star y star and g of x star y star will be equal to 0 because it's a fixed point. And hence, well, finally we can write down u dot and v dot is equal to del f del x, del f del y, del g del x, del g del y times uv. So we have linearized the system near the fixed point, and it depends on the eigenvalues and eigenvectors of this particular matrix, which is also called as the Jacobian matrix. It depends on the local slopes of the functions. Alright, so let us quickly look at the Jacobian of this. So the Jacobian of this will be del f del x, which is 1, del f del y, which is equal to minus y, minus 1, well, minus e to the power minus y. This will be 0, this will be minus 1. And we have to evaluate the Jacobian at the fixed point. So the fixed point is equal to 0, rather minus 1 comma 0. So this is equal to 1, and at 0 this is equal to minus 1, 0, minus 1. Alright, so what are the eigenvalues? So lambda minus 1 times lambda plus 1 is equal to 0. So lambda equal to 1, lambda equal to minus 1. These are the two eigenvalues, and the corresponding eigenvector is going to be, this corresponds to v2 equal to 0 and v1 equal to v1 is an identity. The first eigenvector will be simply 1 comma 0. Second eigenvector will be 1 minus 1, 0 minus 1 is equal to minus v1 v2. So this eigenvector corresponds to lambda equal to 1, and the eigenvector corresponding to this will be, so the other eigenvector will be half comma 1. Okay, so at the equilibrium point, that is minus 1 comma 0, one eigenvector is this, and the corresponding eigenvalue is lambda equal to 1, so it is unstable. At the same equilibrium point, the other eigenvector is half comma 1, which is a slope like this, and it is having an eigenvalue of minus 1. That is, it's an attracting manifold. So this is the stable manifold, this is the unstable manifold. So over on this particular plot, over at this point, this is the linearization. Let me use red color. So this is the linearization uh, that we're looking at. Okay, so the arrows will be like this, but because of the nonlinear effects away from the fixed point, it will tend to become curved, and the curve really depends on what the nature of the equations are. Another important aspect of these points, rather of such curves, they are called as Nullclines. So Nullclines are curves in the phase portrait which correspond to either x equal to 0 or y equal to x dot equal to 0 or y dot equal to 0. That is, they are demarcating curves where we know that there will be either no x velocity or no y velocity. Okay, so if x dot equal to 0, we know that the flow at that point will be solely in the y direction. When y dot equal to 0, we know that across that curve the velocity will be solely in the x direction. So let us try to plot the null clines as well. Okay, it's quite easy to actually plot because we have all the x and y's. So we simply need to plot plt dot contour x1 y1 u1 v1 sorry, x1 y1 u1 and levels equal to simply 0 comma 0. So this is the null cline of x dot equal to 0. Similarly, we want the null cline of y dot equal to 0. Okay, so let us plot this. Okay, so this is the null cline of y dot equal to 0, and this is the null cline. Oh, sorry. Uh, Let me put a different color. Okay, so this is the null cline where y dot equal to 0. So the velocities are only in the x direction. So along the green line, obviously the velocities are in the x direction, while the purple line is the null cline of u1 equal to 0, which corresponds to a line in which there is only a y velocity. And these are not the manifolds. It is not to be confused with the manifolds because those are something else altogether. But the null clines give an idea where the trajectories will straighten or flatten out. Okay, so in this particular example, we have already seen what we expect. So we have performed a simple linearization in order to ascertain, and the linearization depends on the Jacobian. So then the question that people who study nonlinear dynamics they ask is whether the structure of the Jacobian matrix dictates the entire picture, whether the prediction using the Jacobian matrix, that is the Eigen Values and Eigen Vectors, are they strong enough to tell that yes, even the nonlinear system behaves like that? And the answer is it depends. It depends whether uh, you are having eigenvalues real and or the even for a complex eigenvalue, I mean whether or not you have a zero real part or not. Okay, it all depends on the real part of the eigenvalue. We're not going to go deep into this, but for those of you who are interested, you can look up the Hartman Grobman theorem, and it tells you whether or not the linear picture near an equilibrium point is equivalent to the entire picture for the entire nonlinear equation, whether linearization is good enough to make predictions. Okay, so for now we will continue onwards and we will try to have a look at a different set of equations. So let us consider x dot is equal to minus x plus x cube and y dot is equal to minus 2y. Okay, so before anything, let us quickly see how these equations look like. So we don't really care about the null clines for this particular equation, but even before starting, we should be in a position to say how many fixed points does this equation have. So the fixed points are where x dot equal to 0 and y dot equal to 0. Obviously it corresponds to y equal to 0 and x equal to 0 comma. So this equation is x times minus 1 plus x square, and if it is equal to 0, x equal to 0 or x equal to plus minus 1. So we have three fixed points 0 comma 0, minus 1 comma 0 and 1 comma 0. Alright, let us see whether this checks out or not. Okay, so when we look at this particular plot, we see that the trajectories or the streamlines are being attracted towards the origin, while we do have some kind of a hyperbolic flow happening around 1 comma 0 and minus 1 comma 0. Okay, so in fact, let me keep these particular streamlines as well. Along with this, let me plot the trajectories. So let me copy a snippet that we had done in one of the previous example. Okay, so we need this. We need this. All right. So let us take that and so T-span is going from say 0 to 5. The initial points, let us keep this. We have to change the function, so it will be minus x plus x cubed. So it is minus this plus x naught cubed, and this will be minus 2y, and this is already set to minus 2y. So plt dot plot x out comma y out. Okay, so we have written down the code. I've changed the t-span so that the trajectories are not flying off to infinity or minus infinity. And let us wrap this entire thing inside a function. Okay, let us try to put all of this inside a function so that we can probe the different initial conditions. So show traj x naught comma y naught. We will wrap all of this. Okay, x naught, let us give some default values. Okay, that's fine. Let us comment out this particular line. All right, let us create an interactive widget. Minus 1.5 to 1.5 in steps of 0.1. Y naught will be the same. And we'll display the widget. Oops. So here. All right. Let's go. Okay, so the trajectory starts over here. As we change this, so we see that the trajectory can also be shown, and it crosses up to infinity. It's not as entirely feasible to have long trajectories. Okay, so it is quite obvious that trajectories are flowing in this particular manner. Okay, so they are being attracted towards this and they are repelled away from this. Okay, so how can we find out whether, I mean, from theory, what the nature of these points are? Okay, so you can do the following. I'm not going to do it for you. Find out the Jacobian for all these points, and then based on that find out the eigenvalues and eigenvectors. So it should be clear that the eigenvalues, one will be negative, this incoming one, and one will be positive, this one. Okay, so this is a stable node. All the trajectories are converging towards this, in the vicinity at least, and this is again an unstable node. Okay, so this eigenvector should have a negative eigenvalue, this should have a positive eigenvalue, negative eigenvalue. So you should be able to figure this out with the help of the Jacobian. Okay, so let us now move on to the third example where we will see a certain case where such kinds of things may or may not always work. The linearization where it will fail, so to say. So actually we don't need all these stream plots. We can make two with only the quiver plot. Okay, so let me remove all this. We don't need sorry, we need the quiver plot. We don't need the stream plot. So we get rid of this. We have the trajectory solver. Let me keep time equal to 1. Let me just see whether I've broken something or not. Okay, so I've not broken something. It works well. Okay, these are the trajectories. Great. So let us consider this particular problem. So just for the record, the previous problem was rather easy to figure out, and you should be able to find out the Jacobian and the interpretation of the Jacobian with respect to the previous problem. Let us consider this problem. So x dot is minus y plus a times x square plus y square. Y dot is equal to x plus ay times x square plus y square. So this is an example from Stogart's again, but it serves as a very important example where linearization does not always provide a good insight into the problem. But before that, the vectors that we see over here are quite small. In fact, let us fix that. We need to normalize the vectors. So if you have a vector like this, uv, in order to make the magnitude of this vector 1, okay, the magnitude has to be 1, you simply divide it by square root of u square plus v square and square root of u square plus v square. Basically divided by the magnitude in order to render it as a unit vector. So divided by square root of u square plus v square 0.5. Let me copy this and let me paste this. So let us see. Okay, so the arrows look much better. You can sort of visualize things in a better fashion. So let us change the function so that we have this function over here. Okay, so this will be minus y plus a times x times x square plus y square, and this will be x plus a times y times x square plus y square. Okay, so let us pass a as a parameter to the problem. Let it be 1.0 at the outset. Oops. So a will go from 0.8 to 1.2 in steps of 0.05. Let's run this. Okay, so when a is equal to 1, actually it has to go from, let's say it goes from minus 0.4 to 0.4. That's when the fundamental change in behavior will happen. Okay, so this, let it be 0 as the default value. Okay, so when it is 0, you see that the trajectories tend to look like a concentric line, and I've forgotten to change the equations which the initial value problem solver will use. So let us quickly fix that. Okay, so I've fixed it. The time span can be increased to say 5 seconds. Okay, so it does look like it's gonna end up being a closed contour. Alright, so it does appear to be a closed contour. Let me change it. And for all different initial conditions, it does appear to be a closed contour. Okay, so now what happens when I change a ever so slightly? I'm changing it to 0.5 and it has blown away to infinity. So let me change the time span. Let me make it only 2 seconds. In fact, can you see what happens when A becomes positive? The initial point is trying to spiral out. It's not trying to close into a loop. You can clearly see it when I choose an initial point quite far from the equilibrium point. Okay, so first things first, equilibrium point is x equal to 0, y equal to 0. This is a fixed point of the system. Now, when we linearize this, okay, when you linearize this, you're obviously going to ignore the cubic terms. So this term and this term, they're the cubic terms. In the absence of cubic terms, it becomes an equation which resembles this. So obviously, when you linearize the equation, you're losing out on the information which is contained by this particular control parameter. Okay, so when a equal to 0, we've seen that it's a closed orbit. When a is greater than 0, we see that it's a outward spiral. And when a equal to 0, can you guess what will happen? If you've guessed it becomes an attracting spiral, you are correct. Okay, so it spirals into the solution, rather into the problem. Let me just increase the time span a bit so that spiraling in is rather obvious. Okay, so it's spiraling into the origin. Let me increase the time span even further. So we know that it's spiraling in, so nothing's gonna change a lot. Okay, so look, it's spiraling in and looks very nice. Alright, so it becomes an inward spiral. But when you linearize the system, you only get a system whose Jacobian is 0, -1, 1, comma 0. And obviously, this has eigenvalues of 1, comma -1. Rather, it will not have 1, comma -1, it will be purely imaginary. Okay, so the eigenvalues will be plus minus I, and the eigenvalues indicate it will be a closed orbit because it's purely imaginary. So this is the fixed point 0, comma 0, and if you linearize the equation, it will always predict it's going to be a closed orbit. Okay, it's going to be a closed loop. But the dependency on A has been washed away by the fact that we have linearized the system. If we do not pay attention to the entire nature of the equation, it will not work. But again, for these particular cases, okay, for centers, so this is called as a center because it's like a center for a closed orbit. So for degenerate points uh, and such points, linearizing does not give you the entire picture. But for saddles or spirals, um, or what do we have, nodes, so for these particular cases, the linearization does give you an accurate picture of what the equation is going to behave like. Okay, so go ahead and have a look through some other NPTEL courses where they discuss deeply about the nonlinear dynamics part. All whatever I have discussed is a part of the Hartman-Grobman theorem, and that theorem tells you that you can distort the space for these particular geometries or vector flows, and you can obtain a nice solution. But you cannot obtain the behavior using linearization for these kind of particular cases. But regardless of that, Python does give you, or Python or GNU Octave does give you an ideal tool set to really change the value of the control parameter and see what difference it brings into the picture. Alright, so this is how we can sort of look into the problem without really solving the problem. But of course, once you do have the tools, it must be clear that your analysis is of utmost importance. What you can infer from these diagrams. Anyone, so with the help of whatever we're discussing, you should be now in a position to to tell that okay, this is happening or that is happening. But then what physical significance does it lie? That is all up to you. Let us now proceed to another set of problems in which we have an attractor or an oscillator. So in physics, we have what is called as a conservative system, and typically it is defined as m double dot x, and that will be equal to some force. But this force has, if it is conservative, then it can be given as the negative of some negative gradient of some potential. Okay, so let us consider the potential V is equal to minus half x square plus 1/4 x to the power 4. Let us consider this particular potential. Okay, so what is the force? The force is going to be minus x plus x cube. So once we substitute this over here, we have, so let us forget about the m for now. So x double dot will be equal to minus x plus x cube. So let v be equal to x dot, let y be equal to this, and so y dot is equal to minus x plus x cube. Okay, so let me change the particular flows that we have over here. So this is going to be minus x plus x cube. Okay, so we've encoded the entire problem. So let us now run this and see what happens. Okay, when we run this, okay, everything has blown over to infinity. So why is that? So the reason is I've forgotten to take the minus sign over here. So f is minus dv dx, so this actually becomes x minus x cube. So this will change and this will change. Consequently, our code has to change as well. Well, just don't make this kind of mistakes, at all I can tell. Okay, so now we have the trajectory which looks something like this. It looks quite nice, and when you reduce the, change the initial condition, you suddenly have this kind of change. Okay, so now let me, it becomes a lobe and then two lobes and then it grows into a single orbit. Okay, so it's quite obvious looking at this diagram that there are actually two fixed points. Well, by now you should be more than able to tell me what the fixed points are. The fixed points are points where x dot equal to 0 and y dot equal to 0. In this case, y equal to 0 and x will be either 0 or plus minus 1. So these are the fixed points. So minus 1, 0, 0, 0, 1 comma 0. And what is the behavior of the equation near the 3 points? You should be able to tell me with the help of the Jacobians. Okay, but regardless of that, it appears if you look closely over here that this point is attracting, this point is repelling. In fact, let me reduce the number of arrows so that things become slightly uh, clearer. Okay, yeah, well, this is perhaps too few arrows. Let me make it 15. Oftentimes it all depends on how you can interpret the equations. Okay, so it's something like this at the origin. So you have something like this and this, and something like this and this. Okay, so you have this at this point. We can change this and see. So this trajectory is going around in circles, Okay, so there's a bunch of closed orbits over here. Similarly, there's a bunch of closed orbits over here as well. Okay, so essentially it's like you have a closed orbit like this, closed orbit like this. They're going in circles like this. Okay, the picture is more or less like this. So this is a saddle node, this is a center, this is also a center. Okay, so this is the entire phase portrait for this particular plot. So what happens when we change the different initial conditions? You see that uh, if you choose an initial condition over here, it will not go into these centers, but it will have a separate orbit which sort of envelopes this entire set of inside orbits. But if you choose an initial condition over here, it goes around in circles around this center, or it goes around in circles around this center. But once you are having an initial condition over here, it goes around in circles about this center, but it encompasses all the fixed points. So what really is going on? So such kinds of systems are called as conservative systems for a good reason. So this particular equation that we have, okay, so x double dot is equal to x minus x cube. Let us multiply this entire thing by x dot. X double dot x dot is equal to x dot minus x cube x dot. So now this is half of x dot square dot. This is going to be half of x square dot, and this is going to be minus 1 by 4 x to the power 4 dot. Okay, so this implies ddt of half x dot square minus half x square plus 1/4 x to the power 4 is equal to 0. It means that this entire term is equal to constant, and let us call this as the energy. So energy equal to constant. So given this differential equation, the solution in the phase space must also satisfy this additional constraint, if you will. Okay, that the energy along any contour is going to be conserved. If you choose an initial condition, that is x naught at 0 and x at 0, once you choose this initial condition, you are setting or you are dialing in what the value of the energy has to be. Once you dial in that particular value of energy, you simply follow the contour in the phase plane which preserves that energy. That is how you can easily find the contour. Okay, so with the help of this, let me in fact now get rid of the arrows as well. We don't need the arrows. Let me in fact get rid of, let me keep this. Let me copy this and create a new cell, and let us get rid of the contour, the vector plotting, and let me simply have this. All right, we don't need the interactivity in this, and whatever I'm going to do now, let me indent it back and let me remove this. Okay, so it shows a bunch of it shows the trajectory, but if you look closely, the trajectories are really, I mean, wiggling around way too much. You have to increase the number of points to make it smoother. Not only that, let us increase the accuracy of the Runge-Kutta solver. So let me make rtol is equal to 1e minus 6. Great. Now we really have a smooth curve. It all depends on how well constrained you want to make the Runge-Kutta solver. Okay. Smaller the relative tolerance, better will be the smoothness of your solution. If I reduce this to 1e minus 2, look at how errors are being accumulated. Okay. The orbit should not degrade into so many orbits. It should be a single curve. That is why increasing this will really make things look much better. Okay, so now let me create a new variable called as E, and that will be this energy equation that we have, not the equation but the expression for the energy. So it is half times y out squared minus half times x out squared plus 1/4 times x out to the power 4. Alright, in fact, apart from this, let me actually, we've seen the trajectory. Let me show you how energy looks like. Right. So energy is varying over an extremely small bandwidth, and this is due to the errors accumulating in the Runge-Kutta solver. So the energy is decreasing, but it's not decreasing very fast. Over the entire time span, it has hardly changed from 2.8862, 2.88 something plus 5 into 10 to the power minus 6 to something like 2.88602 plus 1 10 to the power minus something. So for a mean value of around 2.88, it's changing by 10 to the power minus 6. This is really quite negligible. And how can you show that it's negligible? You simply change the y limits of this plot. So you do plt.ylim and say you go from 0 to 2 or 1 to 3. It's almost like a straight line. So the energy is hardly changing. So we now know that along a certain trajectory, the energy is not going to change. Okay, can we somehow connect this particular phase plot? So let me make a new page. So the double well potential actually looks something like this. Okay, so this point is -1, this point is 1, this point is 0. So as you can imagine, if you have a ball over here, if you try to roll it like this, so it will try to oscillate like this, and this particular oscillation is nothing but this particular trajectory. So as it's oscillating in this potential, it gives this trajectory in the xy plane. If the initial point is somewhere over here, so let me just track this over here. So then we have this trajectory and it corresponds to this trajectory. But now if I increase the velocity, even if I start over here, it will sort of cross the barrier. Alright, so it is having enough energy to oscillate all the way from this to this. It's doing this oscillation, and that corresponds to this entire sort of closed orbit. But if you have small energies, you are only oscillating inside the neighborhood of 1 and -1, and hence you see that. So uh, can we actually plot this? I mean, obviously you can sort of make the connection that this phase plot and the potential, they do have a certain thing going on over here, something like this, and trajectories like this. Okay, so what is this center point? That is called as a homoclinic, not that point, rather this particular orbit is called as a homoclinic orbit or a homoclinic trajectory, because the trajectory starts from this point and it ends at this equilibrium point. Okay, so whenever a trajectory originates and ends at an equilibrium point, that particular trajectory is called as a homoclinic orbit. Okay, so this corresponds to this, this small oscillation will correspond to some internal oscillation similar to this over in this lobe as well. But can we plot it in the energy space? So imagine if I were to plot energy on this axis. So when we have small oscillations, these are oscillations corresponding to low energy. Okay, so there will be small lobes, but when you have large oscillations, then the trajectory is whatever is shown over here. So can we show that? Can we arrive at some kind of figure like this? Let us see. Let us see how to do that. So this is the plot that we have. Let me copy this, or in fact, let me copy this over here. So now we have X, Y, and energy. So we will do mlab.plot 3D X out, Y out, E. So let me see what this looks like. So we have to do mlab.show as well. Okay, so we have this trajectory, and this trajectory is actually corresponding to this trajectory. Okay, so now let me choose a series of initial points and let us reconstruct this entire three-dimensional phase space. Well, it's not strictly speaking a phase space because E is basically a derived quantity from X and X dot, basically X and Y. But still, it gives you a nice picture of how the double well potential connects to these trajectories. Okay, so I'm just gonna pick this up. I am gonna make a loop. So for y naught in np.linspace 0.1 to 2.5 in steps of say 0.1, I'm gonna indent whatever is over here inside, and lastly I'm gonna show that plot. Let us run this. Let me close this. Let me run this. Okay, there's an error. What is the error? Oops. So obviously this has to be a number of intervals. Let me keep 10. Okay, so look, let me enlarge this. So this is that limb. Okay, this is that limb where it is confined to the low energy oscillations. As we go towards higher levels, we have these outer orbits. In fact, let me increase the number of contours so that it will be even clearer. Okay, so this is that initial condition, and as y increases, it transitions from having these small orbits. So this is like the heteroclinic orbit. Okay, it's just about to touch, and you might be wondering why this orbit is not there, because I'm not starting initial points over in that part of the loop. Okay, so I am starting my initial conditions over at, okay, so I'm starting the initial conditions somewhere over here. Okay, and as I'm slowly increasing y, I am transitioning into this double lobe and finally into this continuous band. And this is exactly what we see through this particular diagram. Okay, so in fact, it will be nice if we can color these three-dimensional objects. So let us do that. In fact, in order to color them nicely, let me first output what the value of the energy is, and I'll tell you why I'm doing that. So let me just print mean of E, because energy is obviously going to be preserved along, it's going to be preserved in time for a given initial condition. So I don't find any utility in printing out the entire string of energies for a given initial condition. So I'll just print the average energy for a given initial condition, because we're looping over all the different initial conditions. Okay, so let me close this. Okay, so it's starting from minus 2.23 minus 2 point, so let's say minus 0.3 to 3. Okay, so the energies are going from this. Okay, so color equal to, and we have to interpolate between minus 0.3 to 3. So what we want to pass to color is a tuple RGB, right? Something like this. And we want to map the energy to how the color changes. So we want to map, so the minimum is, suppose this is the energy axis and this is the color axis. So it has to go from 0 to 1 over here, and minus 0.3 to 3 over here. So we want a linear variation in color like this. So obviously C minus 0 will be 1 upon 3.3 times E minus of this, so E plus 0.3. So let us encode this color over here. So this will be color equals 1 upon 3.3 times np dot mean of E plus 0.3, and the other colors we can keep as 1 and 1. Let's run this and see what happens. Okay, so the diagram looks something like this. It's more colorful, and yeah, the whiter the diagram becomes, the more energy that particular trajectory has. The bluer it is, the lesser energy it has. In fact, we can change this further by pasting this for the other color channels as well. Okay, so let us run this. Okay, it's all blackish. We can in fact invert this to get some other color scheme. Okay, yeah, then this looks good. So this is how you can make this kind of curves, and you can show the entire physics of how changing the energy is changing how the trajectories look like in the xy energy space. Okay, so with this we end this particular lecture. There's been quite a lot of things we've discussed. In the assignments there will be questions which will ask you to make use of these tools to delve deeper into certain problems which are of interest to biologists, or it deals with some other kinds of problems which you might have done in class 11, for example. And it will, hopefully, whatever you have done, it will enable you to delve deeper into the science and the physics of it. So with this I end this particular session. I'll see you again next time. Bye.